So in problem number 17, we're going to make this can, and we're going to try to minimize the amount of metal that we use to make this can. If you don't think this is a really big idea or a really important idea, has anyone noticed that the size of the water, bottled water caps are now smaller?
Yeah, and they're really hard to open.
That's friendly. Please fix that.
I'm waiting for Maddie's to go off. They already did. Okay. Then I don't know what I'm waiting for. All right. So, so what we have is that this volume of this can has got to be 1,000 cubic centimeters, or 1 liter. And they're noting that the can is actually going to be cut out of pieces of aluminum, and that the area of aluminum that's going to be used, I'm sorry, I just set, that's what I was waiting for. I set mine to go off at 13 before the hour too.
You're a bunch of posers now, Daddy.
So there's the amount of area that we're going to use. And the question is, what is the ratio of R to H that will give us the smallest amount of aluminum? They're recognizing, by the way, that the two bottoms are going to be cut out of a square piece of aluminum, and there's going to be waste on the ends, on the outside edges. All right. So we've got area is a function of two variables. I suppose we need a relationship equation. Would you please, with your partner, find the relationship equation that ties the H and the R values together? Another equation outside of the function, the minimizing function, that ties H and R together. Is it going to be the volume? Yeah, it's going to be the volume. You're trying to regain from the memory's volts the volume equation for a right cylinder. For all solids, one thing to remember is if it's a prism, then it's going to be the base area times the height. So if you want to think of that right cylinder, it's got a base area which is a circle, which is pi r squared times its height, h. So there's your relationship equation. Solve for your variables and rewrite the area equation in terms of a single variable, please. Remember, A is the thing that we're going to try to optimize. By the way, of the many qualities, good qualities my son does have, is the ability to play the Lego games on Wii. So I downloaded, without him knowing, the iPhone Lego Harry Potter app, and I'm going to go through it once before he has a chance to look at it. So I look at the genius and stuff. But I have to do it when he's not looking. So. Okay. If we solve for H, 1,000 over pi r squared. If we solve for R, we end up with the square root of 1,000 over pi h. You know where my you know where I want to go with this, right? Oh, I thought I was gonna just the square root just despite what you said. Okay, clean up derivative, please. this is the concept, yes, chi-squared is Kleenex patrol. Hold on. Who sneezed?
It's really awesome when you do that, Michelle. I wish every teacher did that.
Okay, fellas, are you sure you that? Yeah, yeah. And so those, yeah, this one does clean up really nicely. We're going to end up with a 2,000, but these pi's cancel, and we end up with 2,000 over r, I think. I think that's what I get.
Yep.
Which kind of begs the question, why you were asking about pi squared. I got a pi on top and a pi on bottom that cancel. Okay, how about a prime? 16r minus 2,000 over r squared. Yes, it kind of looks like that other problem that we did. So algebraically, this might be a little bit easier the second time through. Go for it. Is that going evenly? What do you got for me?
It's 125 is our cube, so r is 5.
Whoa, they're all connected.
Yeah, I don't like it when it does that. Okay, and so therefore r is got to equal to 5? Why am I uncomfortable with that answer?
Because it was saying that's what we got last time, maybe?
No, I just...
Because it's too perfect.
Quiet out there. Yeah. 2 quiet. Okay, no, we're good.
It's right?
Well, let's say it has the possibility of being right. If that's true, that means h is equal to 1,000 over pi times 5 squared, or 1,000 over 25 pi, and 25 goes into 1,000 40 times. So 40 pi. Now the last thing they ask is, what is the ratio of h to r? It's 40 pi to 5. Of course, we can do a simpler ratio than that. 5 goes into both of those evenly. So the answer that they have in the back book is 8 over pi to 1. I divided both of those ratios by 5 and made a simpler ratio. I think that's it. That's number 17. 18.
Why did I randomly fail that?
Are we good? Excellent.
So in each of these examples, we're looking for two equations that apply to the variables being used, so we can isolate one of them.
Okay, no, this would be good because we don't have enough time to do another problem. So let's see if we can summarize the kinds of trends that we saw. Okay, almost every single one of these problems had a relationship equation because the function that we were trying to maximize or minimize was a function of two variables. That's not always going to be the case when we start out with a function that's of a single variable to begin with. But when we have multiple variables running around, there's always a relationship that will get us down to a single variable. Remember that we're looking to take the derivative, set it equal to 0, because that's where the optimization happens. On these problems, when there's only a single critical value, it's going to be the answer. Watch out when you have multiple critical values, because one of them may be a maximum, the other one may be a minimum, and you want to make sure you get the answer for the problem that you're actually trying to solve. We're not trying to figure out what's the maximum amount of metal we can use to make this thing. Yeah, because it's unacceptable to use more metal than necessary. All right.
How would you find the maximum though?
Well, actually,
Like, if it's setting to 0,
in this one, there is no maximum amount of metal. We keep make it increasingly bigger and bigger and bigger.